Stop the transcription. The transcript. Share the screen. Okay, so you can use the presentation mode. Okay. Okay, welcome back. So now we start this second session of this morning. So the first presentation will be delivered by Toni from the Istituto Tecnologico de Gran Canaria, and he will present a state-of-the-art of photovoltaic reverse osmosis, which is quite essential for within the framework of the technologies that we are discussing today. So please,
thank you so much. Buongiorno, good morning to everyone. Well, I will just make an overview on the state-of-the-art of PV designation. The first part of my presentation, I will be quick because the most interesting information is in the second part. So those are the topics that I will explain. I will begin with just an overview of the solar PV-driven aero designation introduction, just to see that we have been for more than 4 decades combining different designation technologies with different renewable energy sources. I will give a brief introduction to the basic theory of solar PV. The same for the reverse osmosis process. I will briefly explain the differences between brackish and seawater designation. Then the most important part of my presentation will be the second part. I will explain why the need for solar designation, and most important thing, the challenges we must face when we want to combine those two technologies. Afterwards, I will explain the PV equipment, some machines, and possible configurations. I will get into some detail with the codes, and more important, are the non-technical aspects. Okay, I will make recommendations if you, in the near future, you want to work in projects, developing projects, combining different designation technologies with renewable resources in developing countries. You have to take in mind this type of non-technical aspects. And I will finalize with some conclusions. Well, here we can see that this is not a new thing. For more than 40 years, combining PV with aero. The first PV aero designation plan was tested, was installed at a commercial scale in Jeddah in 1981. Although research on PV aero designation system began in the early 80s, as you can see in the table below, its precise techno-economic feasibility assessment has been made recently in the last 5-10 years. Here you have some highlights of PV-driven aero plant development. As I told you before, the first solar PV seawater reverse osmosis designation plant was installed in 1981 in Jeddah, Saudi Arabia. 3 years later, there was the use of an energy recovery device. Later, I will explain the great importance of this type of devices in reverse osmosis designation in order to lower the specific energy consumption of the process. In 1988, it was the first PV-driven brackish water reverse osmosis designation. In 98, an hybrid brackish water PV with solar steels. In 2001, the introduction of PV-powered brackish water row without batteries. I will also explain the differences between managing this type of combinations with a backup system of batteries or with a batteryless system. And in 2 years later, in 2003, the first batteryless for seawater PV row designation. And finally, I would like to highlight this one. This is the Sol2H2O patent, that is, which ITC is the owner. This is the first system that we installed in Tunisia, in Sargilene, and it's been working since June 2006. Actually, nowadays, it's still working. It's a brackish reverse osmosis designation, PV designation plant to supply around 300 inhabitants in the desert of Sargilene in Tunisia. Okay. So, as I told you before, PV-powered aero is considered one of the most promising forms of renewable energy power designation. You can see here that almost one third of all the different combinations installed around the world are PVRO desalination plants. Here you can see a scheme of what the diagram of PVRO with battery system. We have the PV solar panels, the temperature regulator, in this case, the storage batteries, the inverter that feeds the high pressure pump. Afterwards, I will explain deeply all the reverse osmosis process and how all more than 70% of the specific energy consumption is fixed in this part of the process, okay, in the core of the RO desalination process. Well, why PVRO is one of the most widespread combinations used? Because both PV solar energy and RO are mature technologies. You can find a wide commercial network of manufacturers and suppliers. That's very important. Here we can find all the desalination plants, both for brackish and seawater desalination. We have brackish water in green color and seawater in red color that have been installed. You can see in this map that more or less it coincides. You can overlap the maps that were showing before our colleagues Pedro and Federico, and you can see that they coincide more or less with the areas where you have water scarcity and a lot of availability of sanitary radiation. Here you can see some selected specifications of currently installed solar PV power plants, both brackish and seawater desalination. I would like to highlight the most recently one in Al Khafi in Saudi Arabia Kingdom. This is a large-scale PVRO, seawater PVRO desalination plant that has been commissioned. In the presentation today, I will just talk about small and medium-scale desalination, okay? But tomorrow, in the group 3 of the First School working group, you will have the opportunity to face the challenges to upscale in PVRO desalination to the large scale, as this one. This is an interesting slide because here you can see that solar PVRO together with wind RO go in the range from some liters per day to 100,000 of cubic meters per day. Take in mind that the area in green, we're talking about off-grid system, small-scale desalination, small, medium-scale desalination, mainly in areas with water scarcity, with no electrical grid. In those regions, it makes sense to install this type of systems. When you go, you upscale in the water production capacity of the systems, you have to go to on-grid systems, and you can see the main message is that PVRO is the most widespread combination. You can see here that we go from the basic research to the application technologies and in the low scale up to the large scale, okay? For large scale, it is desirable to combine PV with wind RO in order to improve the system. Well, just to be quick, a brief review of solar energy. Well, as you may know, the solar energy received from the sun mainly depends on the location and the inclination of the reception device. As you can see very well here, the difference between the radiation on a horizontal surface and the radiation in the same area with an optimal inclination. Solar PV energy is based on the electric conversion of solar radiation on a solar cell. This is what is called photovoltaic effect. Free electrons created here by the absorption of photons are in excess in the N layer, this one. And in a semiconductor, these free photons migrate to a lower layer, P layer, thus creating an electric current, okay? This electric current is what will feed our high pressure pump in our reverse osmosis process. Well, solar cells are connected in series to form PV modules, and on the other side, PV modules could be connected in series or in parallel in order to assemble a PV field, a solar PV field. Here you have the current voltage curve with all the values for you find that a PV cell vary according to its voltage under a given temperature and irradiation conditions. We have those values for called reference or peak values, just for peak power, the current, voltage at peak power. You can see we will talk very much on efficiencies. Why? Because we want to achieve the best energy efficiency of the whole process. Now we are on the solar side. Here you can see that the most efficient solar cells are up to 20%. Okay. Afterwards, when I will talk to you, I will introduce on the energy cover devices for the reverse osmosis process. We will see that the efficiencies achieved could be up to 97, 98%. Okay. So here you have the different type of solar cells. In today's market, the most common material used for PV cells is crystalline silicon. You see that the greatest efficiency is up to 20%, but in current research activities, they have achieved higher efficiencies up to 40%, but tested in laboratories. Here in this graph, it makes a little mess, but it's from the National Renewable Energy Laboratory. The message you can take here is that the record of the solar cell efficiency achieved was in 2019. It was a bit higher than 47%, but this was under laboratory conditions. For real conditions, the highest efficiency achieved is, as I said before, close to 40%. Well, I will now introduce the reverse osmosis process. I will just give a good few figures for differencing brackish water desalination from seawater desalination. Anyone knows what osmosis is? Well, osmosis is what you have seen at the left. It's a natural phenomenon that occurs when you put in contact two different solutions with different concentrations, okay? Separated by a semi-permeable membrane. It has a natural diffusion from the diluted solution to the concentrated solution. This difference of height is what we call osmotic pressure. This process can be reversed, but by applying a pressure. That means energy. If we apply a pressure higher than this osmotic pressure, we can make the contrary. We can get diluted water, desalted water, and brine here, okay? Reverse osmosis, as you have heard before, is the most widespread and sustainable membrane desalination technology available today. This is more or less an schematic diagram of the whole process. I will be quick, and after that, I will introduce you a video. I will not reproduce it because it's about 10 minutes, I don't have time, but I will encourage you to see that video because it's a very good tool for know from the beginning of the process to the end, the whole process. Well, here we have the seawater intake. It's the first stage of the reverse osmosis process. It could be done by two ways: open intakes for large-scale desalination, or closed intake by means of beach walls in small or medium-scale desalination. In Canary Islands, for example, up to 98% of the desalination plants get water from closed seawater intakes. The advantage of closed seawater intakes, you have much better seawater intake quality. Why? Because the terrain gives you a previous filtration of the seawater you take. The problem for large-scale desalination, it's difficult to get so much amount of water with this type of intakes. Well, the second stage is the pretreatment. It will depend very much if you have an open intake or a closed intake. For open intakes, you will have to dosify more chemicals, and of course, you will have a dual media filtration and a cartridge filtration. In some desalination plants in the Canary Islands, just working with a cartridge filtration, they do not use this filtration of 20 microns. It's okay. Why? Because they have closed intake and they have a pre-filtration with X-ray. Although technological development of RO has made possible to reduce the chemicals used in the process, at least anti-scalant is still commonly used in order to prevent the scaling in this membrane surface when you're working with high recovery rates. Well, this is the quote I will show it you with more detail later. This is the core of the reverse osmosis process itself. Okay, the system consists of a high pressure pump, the reverse osmosis rack with several pressure vessels housing between 6 to 7 reverse osmosis membranes in series. Very important, the energy cover device, as I told you before. I will tell you the difference between the first energy cover devices that were used 10, 15 years ago and the last generation energy cover devices. And in the case of isobaric energy cover devices, you always use a booster pump. I will explain it later. Some values, the typical operating values for seawater desalination, we used to work between 50 to 60 bar. This working pressure is lower in brackish water desalination. Someone can tell me why?
The stock concentration is lower and you go.
That's it. Because you have to overcome less osmotic pressure. Okay. The recovery rate for seawater desalination is between 40 to 45. It will depend in one stage RO desalination. It is higher in brackish water desalination. Why? Because you don't have so much salt content, and the problem of the scaling is less. Okay, you can go from to 70% of recovery rate. Recovery rate means that for 100 liters or cubic meters of seawater that you get from sea, you will get 40 or 45 liters of per minute of product water. And finally, a very important figure is this one, the specific energy consumption that was introduced before by our colleague. Actually, in reverse osmosis, seawater reverse osmosis desalination, we are around from 2 to 3 kilowatt hour per cubic meter. For those people that will visit our facilities in the second master school, we are now commissioning a desalination plant. It's a project called ProCan 2.0. No, there's a ROC 2.0 from desalination and reverse osmosis 2.0. And the 2.0 is because our challenge is to get lower than 2 kilowatt hour per cubic meter. Okay, we have optimized the hydraulic design, the efficiency of the pumps, of the electrical devices, and we think that we can go for seawater desalination below those 2 kilowatt hours. That's our challenge. Of course, the specific energy consumption for brackish water desalination is lower, much lower. And finally, the process culminates with the remineralization and distribution. Why do we have to remineralize desalted water? Because the permeate we obtain from the reverse osmosis rack is corrosive, and it must be remineralized both for human consumption, but also, of course, for irrigation. The most used remineralization technique is to add a CO2 injection together with the use of calcium beds to introduce calcium carbonate to the water. By this treatment, we can adjust the pH, increasing the hardness and alkalinity. After remineralization, if the water is intended for human consumption, you also chlorine, okay, not for water for irrigation. This is energy breakdown of a typical seawater osmosis desalination plant. As I told you before, you will see that the highest energy consumption is located here. Okay, this is the core of the process. You can see it better, much better here. This is what I told you before, the reverse osmosis rack with the pressure vessels housing between 6 to 7 reverse osmosis membranes in series. The high pressure pump here is where we have to go with a PV field to get the energy, electrical energy. And the main improvement made in reverse osmosis are those mechanical equipment. Those are isobaric energy cover devices and the booster pump. Which is the goal obtained with this technology? We have passed from, we'll see in the next slide, we have passed from an energy efficiency of about 75–80% of centrifugal devices, energy cover devices, I mean Pelton turbine, to close to 97–98 energy efficiency of these devices. Why? Because you don't have energy conversion step. when you use centrifugal devices, you had a conversion of the brine coming out from the reverse osmosis rack. I told you before, you work at 60 bar pressure in the inlet. But the thing is, just in the output, the brine goes out with 57, 58 bar. Just 2 bar of pressure loss inside the pressure vessel. 20 years ago, this brine was directly discharged to the sea. Why? That's the reason why we had energy consumption of 18 kilowatt hour per cubic meter. We were losing a lot of energy in form of pressure with the brine rejection. Okay, the first devices were the Pelton turbines and the Francis turbines with lower energy efficiency, but these devices, they have 2 advantages. They put in direct contact the brine with the feed water, and they manage just lower than 50% of the total feed water with the high pressure pump. That is the device that most energy consumes. And you manage, we were talking about 40% of recovery rate. This 40% of the feed water is managed with this device. And now with this system, you will manage 60% of the feed water with a booster pump. The energy consumption of this booster pump is 10 times lower than the energy consumption of the high pressure pump. There is the second great advantage. You put in direct contact brine with feed water without energy conversion step, and you manage more than half of the feed water with a device that consumes less energy. This is an example of an isobaric energy recovery device. We have this in Izquierda in Gran Canaria, was tested. We have achieved an energy consumption close to 2 kilowatt hour per cubic meter. The advantage of this device is that it's a 4-in-1 device. What do I mean with that? That is specially designed for a containerized seawater desalination plant. Because you have in the same device, you have the electric motor, the high pressure pump, the booster pump, and the energy box device, the isobaric energy device, all fit in one device, okay? What do you think would be the next step that has already been done to improve the energy consumption in reverse osmosis desalination? Because we're talking about efficiencies up to 97, 98. Very close space to improve that. You will never achieve 100% efficiency. The next step is what we call the last generation membranes. Okay, membrane manufacturers have been improving the membrane flux and the source rejection that is very high. In order to, you have 2 options. Working at the same operating pressure, you can produce more water because you have improved membrane with more flux, permeate flux, or you can lower the permeate production. You can lower the pressure, but you will lower the specific energy consumption. Remember that the specific energy consumption, by definition, is kilowatt hour per cubic meter. If you produce more water or you work with less pressure, less energy, in both cases, you will improve your specific energy consumption. This is the general scheme of the development and improvements. As I told you before, these were the first energy recovery devices that were used. You can see the specific energy consumptions achieved, and the isobaric chambers came in this scenario of water desalination, and you can see how we have been improving this. This is the device I showed you before. We have been improving the specific energy consumption of the reverse osmosis process. This is the video I told you before. I won't show you because it's about 10 minutes. It's an hyper-realistic 3D video that has been developed by ITC together with the Canary Islands Innovation Agency. It is available. This is you have the link there. This is the English version, but it's available also in Portuguese, Spanish, and French. Sorry, but in Italian, not yet. Well, why do we need soil desalination, and which are the challenges we have to face? Well, the use of this is just to repeat what has been said before by Pedro and Federico. The use of aero designations has grown in response to the water scarcity. Despite the improvements made, I have shown you the improvements in the specific energy consumption, aero still consume a lot of energy. And that's why renewable energy is an attractive solution for three main reasons: to reduce the carbon footprint of reverse osmosis desalination plants, to decrease the running costs, the OPEX, and to eliminate the link between water prices and fuel prices, fuel costs. Whereas the power output of a solar PV field is fluctuating and intermittent, it's not constant, commercial reverse osmosis plant are designed for working 24 hours, 365 days per year. Okay, they only stop for maintenance. That could be a great challenge in order to couple desalination with any kind of renewable energy source. In this case, PV. Well, how can we match the load? Because finally, the high pressure pump is a load. You have to feed with electricity in this case. How can we match this intermittent and fluctuating energy production from the PV field with the required constant flow pressure and power level from the desalination plant? Well, we have four different ways. The first one will be the plant configuration. One of the great advantages of reverse osmosis desalination process is that it's modular. Okay, in many cases, you go, for example, the biggest desalination plant in Gran Canaria is Las Palmas 3. Las Palmas 3. Why is it called Las Palmas 3? Because it has been retrofitted and it started with 20,000 cubic meters per day, and nowadays it has more than 100,000 cubic meters per day. You can modularly go upscaling the production capacity of the plant. Okay, so you can put in the same reverse osmosis rack, depending on the available power of your PV field, you can connect or disconnect, for example, different pressure vessels in the same reverse osmosis rack. Okay, and you can operate the plant in a variable production capacity mode. The second operational strategy, you can introduce variable speed operation by using the variable frequency drive in the high pressure pump in order to put the speed according to available power. That means that you work with less recovery rate when you have less energy, and you can increase it just by using this type of devices when you have more energy. Of course, an accurate control system will be needed, and including a backup system. Later on, I will explain the differences, as I told you before, on using a battery backup system or batteryless system. Mainly, you can connect to the electric grid if you have a good connected electric grid. I was talking to you before of a project we had in Sharjah, Tunisia. There we didn't have any option because there was no electric grid. So you had to go in an isolated PVRO desalination. Energy or water storage are also important in order to couple these two technologies, or in any case, you can use also diesel generators. The two main technical challenges to be faced when you operate aero plant in this continuous way. This is some contradictory, you will find, but in literature, you can find that the negative for the first drawback is the shortened aero membrane lifetime. Okay. The negative aspect is that continuous startups and shutdowns and the flow variation and pressure fluctuations can lead to mechanical fatigue and with a negative affection to the membrane lifetime and performance. On the other side, some authors find that this could be positive. Okay, we have a project in Puerto Izquierdo in Gran Canaria testing the performance of reverse osmosis desalination plant by putting the plant in operation. In 2 hours, we stop it. 2 hours later, we put it again in operation. And around 6 months, we studied the performance of the reverse osmosis method. Okay. Many people think the effect is negative, but you can find some authors that report the shorter lifetimes while others highlight improvements. Why? What do they argue to highlight improvements with this type of operation? Because they think that the turbulence improves the diffusion through the membrane and decreases the effect of concentration polarization in the membrane surface. Okay, that thus increasing the flux, the permeate flux, and the quality of the permeate. This is it depends on the opinion of each one. I am more on the side of the negative effect. Well, the other challenge is to reduce the reduced performance of energy recovery devices. I showed you before. The positive aspect is with isobaric devices, the last generation devices. These ones can operate at nearly constant efficiency. They don't lose those 97% of efficiency with a varying flow rate. That is not the case of centrifugal devices, the Pelton turbines or the Francis turbines. Additionally, the decouple operation from the high pressure pump, as I showed you before, you only manage the 40% of the feed water with this device, with the high pressure pump, and the 60% with the booster pump. This is also positive for this type of devices. In the negative side, the effects of mixing and leakage. Remember that you are putting in contact, direct contact, brine, is very high concentration in salts, with seawater in this case, with feed water. It could be up to 5% of mixing through these two flows, okay? And the negative aspect is you can increase a little more this mixing by this type of operation. Well, the PBRO. Okay, I will run. Okay, sorry. Well, a general scheme, a PV field, the charge controller, the inverter, and the loads. The main load, as I told you before, is the high pressure pump. Well, the DC voltage produced by the PV field goes to the batteries, to a charge controller, in order to guarantee a good operation of the batteries. The energy from the batteries is converted to AC in the inverter to supply the different loads, in this case, the high pressure pump. The core components we have shown, and there are two configurations, okay? We'll run here. The first one is off-grid PV designation. You can see here the PV panels and the use of battery backup system, the charge controller, the inverter, and the aero plant. This is used for small, medium destination plant capacities. You will need storage of water energy to overcome the variability of energy resource. High investment cost, depending on the cubic meters produced. It requires an acquired control system, and it can be hybridized or combined by DSL groups. The other system is on-grid, if you have an electrical grid designation. In this case, renewable energy sources could supply a percentage between 30 to 60%, depending on the renewable energy source you are using. And the thing is that this surplus energy can be sold back to the grid in some cases. It will depend much on the country regulation, okay? Here is an innovative design. For those who are coming to the second phase school, we will try to show you this destination plant is now being commissioned. Okay, this is what we call serial discharge using variable frequency drive DC bus. Okay, in this case, the PV is directly connected to the DC bus of a high pressure pump variable frequency drive. In this case, we can save up to 30% of electrical energy from the grid, 100% of the use of solar energy, and the solar field voltage should be adapted to the inverter voltage. Well, I told you before the differences between the PV row with production capacity, that means with a battery backup system, and the other case with battery-less system. Here you have the different advantages and disadvantages. In our case, the sole patent is using this type of design, okay? Well, non-technical aspects of PV road designation include economical, environmental, social, political, and legal aspects, okay? Decided water cost, the current water cost for small scale. Remember, we are always talking a small, medium scale designation in this case. For seawater reverse osmosis grid-connected designation plan is between 1.3 euros per cubic meter, considering this price in energy, okay? During the last decade, PV modules costs, as Pedro told before, have been reduced considerably, and this is a clear benefit for PV row systems investment costs, where the ratio of isolated peak power installed has decreased from 10 euros watt peak in 2007 to around 3.5 euro per watt peak, including panels, converters, power control, batteries, and the place. Depending on the scale and the energy required, for a PV battery system, the cost of water produced is between 1.5 to 4 euros per cubic meter. The first figure for brackish water desalination, the second for seawater. Lower prices that an isolated location could be paid. What does it mean? In the case of Sargillen, that I told you before, the only water available was coming once a week by a solar by a tanker, by a lorry. The price of the fuel of the diesel from the lorry was makes that the cost of water was higher than 12 euros per cubic meter. In those scenarios, it makes sense to install this type of PV row systems. Well, just for as a main message, it is competitive cost in isolated areas where the cost of desalinated water produced with a diesel generator with weak electrical width or with not grid is around 2 euros per meter. The cost of desalination system is high in comparison with conventional desalination costs, lack of clear market and risk understanding. You can read, I will not go in deep on this. The main recommendations for desalination projects with renewable resources is just to design simple and robust, adapted to local conditions. And as conclusions, you can say that PV powered road desalination is a mature combination, a technique for feasibility of the design concepts. It is indeed a competitive solution using this coupling in isolated areas. As I told you before, due to its the mobility of RO, it can be easily adapted to the available energy. The PV panels cost reduction has also been a good thing. PV row connected to grid has an effort and a reduction of between 25 to 35 operating costs. And the main challenge is the connection of this type of systems to microgrids and control the energy loads. I think it's all.
Oh, thank you. Thank you so much. Very broad presentation on the state of the art of this technology, photovoltaics coupled with reverse osmosis. We are a little bit behind schedule, so maybe we have time for one question, if any, from the audience. Well, if not,
I have many questions,
yeah,
but I will ask you that.
Just
one. When you talk about the maximum scale of PV seawater reverse osmosis, I mean real counting, apart from those.
The maximum scale in off-grid or
off-grid.
Off-grid, you will go to the medium scale. It will depend, but on the location. But we are talking about 15,000 cubic meters per day.
15,000.
15,000.
So it's quite large. Can serve.
It will depend much on the site, but it's better in off-grid desalination to go to the small scale. You see in the table I show one of the slides, the maximum are 5,000 cubic meters per day.
Okay, but if we talk about
For larger dissolve system, just to take in mind, is now commissioned last year in Cape Verde, which is a 400 cubic meters per day desalination plant. No,
okay. But for an isolated community of 1,000, 2,000, 3,000 people.
For seawater desalination or for brackish water?
For seawater desalination,
we will have to go.
feasible.
No, not 15,000 cubic meters per day.
No. I'm talking about 5,000 inhabitants, which means 1,000 cubic meters per day.
Isolated from the grid. You will have to go lower.
Okay. Thank you.
Okay, so thank you again, Tony, and then we shall move now.